In this video, we're going to convert a vector between magnitude, angle, and unit vector notation, and then we're also going to add and subtract vectors in both of those notations. And then finally, we're going to identify for a given vector that rotating the coordinate system about the origin can change the vector's components, but not the vector itself. Let's start off with a unit vector. And this is going to be something that's a little new, especially the notation. We say that a unit vector has a magnitude of 1. And so the length of the vector is 1. And it has a particular direction. It lacks both dimension and unit and is labeled with this hat symbol. We are typically going to use the right-handed coordinate system. And what that means by the right-handed coordinate system is that we have an X and a Y plane, and then using your right hand rule, you can see that the Z plane, the three-dimensional space in the Z plane, will come out orthogonal to those two axes. And the unit vector points along the axis. So the unit vector that is just one unit along the x-axis we call I hat. And the unit vector that is one unit along the y-axis we call j hat. And the unit vector that is one unit along the z-axis we call k hat. So that means we can take any vector, say we have some vector A, and it can be broken up into components along the x-axis and the y-axis, which before we would call a sub x and a sub y for those x and y components. We can now take that number and attach an I hat to it so we know that that is the x component, and attach a j hat and know that it is the y component. And so we would have a particular vector that let's say is 3 units in the x direction and 4 units in the positive y direction. And so our vector would be 3 I hat plus 4 j hat. We could use the Pythagorean theorem to find that the magnitude of A is going to be 5 because it only has 2 dimensions, the x dimension, y dimension. Use Pythagorean theorem and we get 5. But what this tells us is right now in this unit vector notation, this tells us how many units the vector moves in the x direction and how many units it moves in the y direction. So it's a way to give the components and also give the orientation and direction of the vector. Because remember, as we stated in the last video, components can tell the whole story of the vector. So components are fully sufficient to describe a vector. A few more notes about these quantities, AXI and AYJ. Well, these are vector components, like we said before, so they're the x component and the y component, but the important thing is those components are scalar. So AX and AY alone are just magnitude numbers. So it tells us nothing about direction, they're just magnitude numbers. And then by attaching the I hat, the j hat, or if we're talking three-dimensional space, the k hat, then that tells us the orientation and what direction that quantity is moving. Now, you might ask, why are we doing this? This is making a vector where we just said, magnitude of 14 newtons at 23 degrees from the horizon. That was simple, that was just a magnitude and direction, whereas now we're making it more complicated. Well, what this does is this allows us to add the vectors together much more easily by just adding their components. So if we have multiple vectors that we want to add together, if they're in unit vector notation, we can simply add all the I hats together, add all the j hats together, add all the k hats together. And later in next section when we talk about multiplying, especially one of the particular cases of multiplying vectors, this vector notation is imperative. I want you to take a look at the figure over here and answer these 3 questions. The first one being, what are the signs of the x components of vector d1 and vector d2, and what are the signs of the y components of those 2 vectors, and what are the signs of the x and y components of the 2 vectors combined. So it may help to find the resulting vector, which you would need to draw here, the resulting vector, and so this is d1 plus d2. And so use that and answer those 3 questions. Pause the video for a second, write down your answers, and then push play to check. Okay, let's take a look. First off, if you look at D1, what are the direction of the components? Well, D1 is going up and to the right. So those are both positive in the x direction and the y direction. Whereas D2 is going down and to the right. So it has a positive x direction but negative y direction. So the answer to the first question in what are the signs of the x components of D1 and D2, they're both positive because they are both moving to the right. And that can help us in part C in what's the sign of the x component of D1 plus D2. Well, if 2 vectors are both moving to the right, you add them together, the resulting vector is also going to be moving to the right. So this is going to be positive. And for the y components, D1 is moving up, but D2 is moving down. And so D1 has a positive y component, and D2 has a negative y component. Now, what about the result of adding these 2 together? Well, if we look at the graph and we see that the resulting vector is moving to the right, but it's also moving up, which we, remember, would know that it should move to the right, knowing that the 2 positive x components add together to continue moving to the right. But it has an end result of up because D1 has a greater y component than D2 does. And so the answers to A are positive, positive, B, positive, negative, and C, positive, positive. This can be done graphically or just analytically reasoning through the different components of the vectors. Vectors are independent of the coordinate system used to measure them. And so we can rotate coordinate systems without rotating the vector, and the vector remains the same. And you've seen this think back to when you first learned dynamics and you drew free body diagrams, especially with objects on an inclined plane. Objects on an inclined plane, a lot of times it was more convenient to change the coordinate system so that the x-axis was parallel to the inclined plane. And so you changed the coordinate system, but that didn't change the vectors at all. But what that did do was it changed the components of the vectors so they were more convenient. We had a component of gravity that was parallel to the inclined plane and one that was perpendicular to the inclined plane, which corresponded with the normal force. And we'll get into more free body diagrams when we reach dynamics in this course. But that just gives an illustration that we can rotate the coordinate system and it doesn't change the vector. And so looking at this vector that we have here in part A of the diagram, we see that we have some length A for vector A, and it's measured at some angle theta off of the positive x-axis. Well, if we rotate the axes, so we rotate the x and y plane such that we displace it some new angle that we'll call phi, okay, that is going to change the angle that was once called theta, which we'll now call it theta prime, even though the A vector did not move. A vector stayed put, we just tilted the axis. Now our components change. We had a small x component here, but by rotating the axis, that made a bigger x component in the second situation and a smaller y component than what we once had. But it still keeps A the same. The vector does not change, just now the components have changed because our perspective has changed. Now, if we want to know how do theta prime, and phi relate, well, theta has to equal that change in the rotation of the coordinate system plus the new theta or theta prime.